Thank you very much for this opportunity of presenting this joint work in progress. This is the plan of our talk. Just read the main point, then during the second part I will come back to deal with this. This is a case study, many challenges, both historical and historiographical. We focus on, which is common mathematician versus elite, focus on partially unsuccessful boy versus classical students, mathematics in paper and also in textbooks. How does the notion of mathematical culture apply in this case? So I'm going to introduce the protagonists of our story. We have two groups of mathematicians called by historians of mathematics the vectorialists and the tensorists. This is the main characters, and there are also some minor characters in this group. So I mentioned the first two mathematicians came from Turin and belong to Peano's tradition. Burgatti is was professor at the University of Bologna of mechanics, Marco Longo, the professor of mathematical physics in Naples. Among the tensorists, the main character was David Civita, and of course then many of his students. An important debate took place at the end of the 19th century and involved several mathematicians and different traditions. The problem was to find a common notation for vectors and vector calculus. In fact, each country proposed one or more vector notations, and also in Italy, vectorialists were very active, and especially, in particular, Forte and Marco Longo proposed the so-called minimal system. David Civita encouraged vectorialists to take part in the international debate. You find some debate concerning international debate. In any case, stopped at the Congress, International Congress of Mathematicians in Cambridge in 1912. And then, because the World War I broke out, there was a stop. And the question of finding a common notation so did not find any answer. But it is interesting for our story because vectorialists looked for an intrinsic notation of vectors. As you know, a vector can be seen also as a set of two or three numbers. It depends on you consider a vector on plane or in space. The numbers are their coordinates. And the vectorialists, in fact, aimed at considering the vector as an object in itself, so not by means of its coordinate, but here as an object. This is a picture of the system. These are some of the basic definitions of the theory developed by vectorialists. They published many books and papers on the subject. Now I come back to this. This is from the Homographie Vectoriale published in 1909 and then translated into French some years ago. So the basic definitions of their theory were those of vector homography, called today linear transformation, information, and that of linear system, called today vector space. Both definitions have been given also by Peano, but in a more abstract form. The book, Omografie Vettoriali, also thanks to its applications to mechanics, gave an important contribution to what we call today linear algebra. The reception was very good, in fact. I don't read reports, just the report by Cahen on the Bulletin des Sciences Mathématiques in 1921, so many after the publication of the book. He wrote that the book is already a classic. I go on and I try to introduce what is a text just by an example. The example concerns the strain tensor, that is to say, tensor which intervenes and which well describe what happened in an elastic body submitted to some forces. A tensor, in this case, we have a 3 cross 3, a tensor called of rank 2. This tensor is described by a matrix of 3 for 3 matrix, so 9 numbers. Anyway, not all matrices are tensors, because if you consider a matrix, any matrix, you cannot conclude that it is a tensor, of course, because for being a tensor, a matrix must follow a specific transformation law for a change of coordinates. So,
should that be an H there? Should that be an H there? Or am I wrong? I wonder if that should be an H.
Yes. It's IK and GH.
Okay.
Yeah, okay.
Yeah. Yes. In any case, what you can see in this definition, a tensor, this kind of definition defines a tensor by means of its coordinates. Okay, it is not an implicit definition, and this was the way mathematicians of the founder of tensor calculus, in fact, this is a picture of 9 numbers which compose tensor. The founder of tensor calculus was Ricci Bastro in this years, 1880 and 1890. It was the years when he developed his tensor calculus. As the definition of tensor was more or less given as I told you before. It is by coordinates. I don't speak about Medicivita, it's too long. But just to say that it was in 19, as you know, an image, it was in 1915 when Einstein published his papers on general relativity, the tensor calculus became an accepted and studied theory. This is the ambitious project of vectorists. What did vectorists aim to do? So they published, first of all, they published an enormous amount of work, 300 of papers and more or less about 10 books. And they aim translating many formulae and results, basic formulae, results of tensor calculus, so expressed by coordinates into an intrinsic formalism. It is by using his own formalism, his own vector notation. Why? Because they claimed in many papers, always claimed that their formalism was simpler and more elegant than any other formalism, in particular tensor formalism, because their formalism did not make use of coordinates. Okay? So there are also show many applications to mathematical physics to show that their theory was efficient and powerful. The dynamics between the two schools. I just mentioned that usually several historians of mathematics claim that a war happened between the two groups, vectorials and tensors. We don't agree with this claim. In fact, we can show that tensorists use both tensor vectors when necessary, and they always show, we can say, a pragmatic attitude. But on the other side, in fact, we have to say that vectorialists attacked tensorists and tensor calculus, and in particular in a book entitled Espace Court, published in 1924, and also after the publication of this book. So we think that the reason is that the main reason is that they confuse confusion between the theory of general relativity, to which they were opposed to the theory of general relativity, and its formalism, which was expressed in terms of tensor calculus. So, vectorialists, as I told before, defined the concept of homography in a three-dimensional space, because for them the three-dimensional Euclidean space was the physical space and the only space where they aimed at developing geometry. They're interested in what happened in reality. But also they were led also to consider an dimensional space because of criticism against the way of considering geometry, and so they generalize homography in one-dimensional space by defining hyperhomographies. Hyperhomography is what we can translate today as multilinear maps. Okay? And in fact, they clearly pointed out that the concept of tensor is included in their definition of hyperhomography. And they don't understand why this definition of tensor is followed. Is mainly because it is a German denomination, and instead of their own definition of hyperhomography. I have no time here, but I should add that I can show many letters, some interesting correspondence between vectorialists, that social, political, and personal elements enter in this story. This is just a very little example. But, in private correspondence, of course, we are more stronger and harsher. This is one of the modern definition of tensor given by Chevalier in 1955. And this, as you can see, this is an intrinsic definition. I cannot explain more, but just to show you that the idea of a tensor as a multilinear map is modern. I cannot enter in detail, but I just want to show you that vectorialists, in fact, had, of course, a good idea, we can say, but anyway, they misunderstood many basic results and definitions of tensor calculus. This is an example. They never, in Espace Court, for example, where they criticized harsh theory of relativity, where they confused the covariant objects with covariant equations, for example. They never use hyperbolic matrices. You know that you cannot do the theory of relativity without it. And they also proved that Christoffel symbols constituted hyperhomography, that a tensor, but we know very well that it is not true. But I had to add that also some mathematicians coming from the other group, for example, Chisot, proved the same, in this case, the same statement. It is to say that he spoke about Christoffel tensor, and Chisotti published in 1928 a treatise on tensor calculus, and published 1 year later a paper where he spoke about the Christoffel tensor. So, I mean, the misunderstandings about these concepts were wise. We are very, many mathematicians had the same problems. It's not just vectorials. Of course, the reception of this class was not very good. You can image. I just mentioned the report by Reinich, a relativist. This book makes one feel sad. It is an example of how intolerance can mislead even powerful minds in the field where we just some words for what happened after the Espace Court. Vectorialists and their students, because they had students, went on publishing papers and books on vector theory and its application until 30 years. And we can see that in Italy, in the 40s years, some books appeared, were published, some books of synthesis, where we can find both homographies and tensors.
Okay. So now that Rossana has presented the case study, so this one-sided controversy between tensorists on one side and vectorialists on the other side. So the controversy was from the part of the vectorialists against tensor theory, but as Rossana said, not from the part of tensorists. So now I'm going to present you some questions emerging from this case study, which has interested us because it was an unusual, it was a set of unusual aspects in the history of mathematics. The most striking aspect was the amount of publications. You have hundreds of pages. We demonstrating already known results in tensor theory, for instance. And it is weird in a way, because usually one thinks that once a theorem is demonstrated, it's over. Usually you don't work at re-demonstrating it, but then the vectorialists spend a lot of time re-demonstrating and using very clumsy formulae, for just nothing or about nothing. So, we have a first set of questions about mathematical modernity, because there is a sort of contrast between a retrospective or a historical view and the view we can gain when we look at the details of this one-sided controversy. So I've tried to present the contrasting approaches in colors. So on one hand, retrospectively, the vectorialists look rather unsuccessful because they didn't manage to catch up with relativity theory, for instance. They didn't manage to catch up with high-dimensional geometry. So it seems that in some ways they failed. But on the other hand, they also have introduced many tools that we still use today. Linear algebra is still used today, and it's the common language for rational mechanics and many parts of theoretical physics. So there is a contrast here. Second, in a way, the tensorists look more modern because tensors were the way to more general formulation of the theory of general relativity, and so tensorists look as, from a retrospective point of view, tensorists look as the success way to modern mathematics. But what is very interesting is that at the beginning of the development of tensor theory, tensors were judged very uninteresting and unpromising. Most mathematicians looked at tensors and thought it was just a game with symbols, not real mathematics, not interesting objects. So this is the first set of questions about mathematical modernity. We have a second set of questions about intrinsicity. Yes. So, as Rossana said, vectorialists were driven by the quest for intrinsic objects. They rejected defining mathematical objects by coordinates. And so, from one point of view, this is an old quest, a respectful quest, beginning with Leibniz and then Gauss and other mathematicians, including Piano, for instance, and leading to Claude and other members of the Beauvais school, as Rossana said. So, from one point of view, the quest for intrinsic objects is modern. But from the other point of view, when you look at the papers and textbooks and hundreds of pages, you just see very, very unelegant formulae which don't look modern at all. You have demonstrations taking, tens of pages, and it's just impossible to follow because the horizon is so bad. And third, there is also a contrast about the conceptions of space that were discussed in this controversy. First, the vectorialists were attached to three-dimensional Euclidean space and projected spaces of higher dimensions and also general relativity. This was together as Rossana has said. So this is not modern at all, but on the other hand, the vectorial is provided